My name is Maxim. I came here from Berlin, and this is my tweet handle. If you like to tweet something, or if you don't like to tweet something still, this is still my Twitter handle, basically. And what I would like to talk about is beyond JSON, which is an interesting topic. So, agenda. I will tell you a few war stories of mine, and they will have very technical details. Sorry for very technical, but this is basically how I do my presentations. All right, so the year is 2007. Mostly if people hear something about 2007, they think about this, right? So it is basically how the mobile movement actually started and so on and so forth. For me, 2007 is actually a bit different. So in 2007, I just came out of university and started working here, which is an online bank in Germany. And I was a Java developer. I had nothing to do with mobile actually at all. I worked on a product where we migrated the banking parts of the banking application from C and PL/SQL to a new and shiny Java frameworks. And one of the topics which came out was following this: JSON versus XML. Back in the days, XML was like the thing, specifically if you were doing Java development. It is actually still the thing if you are doing Java development. Who's actually doing Java? A few people, okay. So I guess you understand what I basically mean by this, right? And in 2007, we discussed about how should we transfer data between different services, and then I found out about JSON, and I was like, oh my God, it's so human readable. It's so much better than XML, because I suffered through XML for years as Java developer, and then there was something which is like, great, right? But it had some caveats though. It has no schema, so it's schemaless. It can state whatever, right? Nowadays, there is JSON schema actually, but it's also optional, and it's a secondary project which you might use or might not use. So the schema problem still persists even today, in a way. Then there is no streaming parser. In XML, you have basically two ways how you can parse XML. It's DOM parser and Zaks parser. DOM parser means that you basically suck everything in and you read everything, and Zaks parser means that you can actually, it's event driven, so you could say like, okay, I'm interested in the following node, so please read until this node, notify me when you're there, and then I can also tell you to break up. So specifically if you have lots of data, you could basically say like, okay, I'm interested only in a part of it, not everything, right? But actually what defined the conversation was the last point. It was too early for financial sector. So with all the ideas that I can, all the good things and bad things, basically at the end we just said like, okay, we are in the bank and JSON is new, so no. And this was the end of the conversation, basically. Let's skip to 2015. I'm not on the, working at the bank anymore. I'm actually working at a gaming company in Berlin. And what I'm doing there is, for the last 3 years, is simulation games. Simulation games means that we're building some kind of a city, and so on and so forth. And it's basically simulating. This also means that we have a deterministic simulation running on the mobile device, and then it has to be validated on the backend. Why is it like this? It is like this because we would like to prevent cheaters. Because basically we can't trust front ends, because you could hack it and you could start doing things that you would like and actually harm other players. Specifically, if you have a social component in the game or even a competitive component in the game, everything has to be validated with a backend. Meaning that basically I tap something on the mobile, we send a command to the backend, and backend said, OK, you could do this, yes, that makes sense, and so on and so forth. So we basically spamming our backends enormously, right? In the last project that I worked on in 2015, the backend developers were introduced a little bit later, so like half a year into development. Therefore, we were already pretty advanced in our simulation logic on the front end, but they just started from scratch. So we kind of losing half a year of development time, in a way. So we thought about it and said, like, what if we would share code between backend and front end? Because it's still a simulation, right? Basically, a simulation is you take a game state and a config, then you apply a couple of rules, and you get a new game state. This is it. Meaning that if you have a deterministic simulation on your front end, it could potentially run as it is on another platform and spit out the same result. In a way, just a function returning the same result here and there. And therefore, you can validate easily. So what we came up with was, we say, let's create a stateless worker, meaning that it will be just a process which runs on the backend, which gets config and game state and a set of commands, and it will return a game state back, which then will work stateless. This was kind of a scary thing to do, actually. Why is it so scary? Well, because normally what we do on the backends is stateful backends. Because as I mentioned this previously, every tap, every interaction goes to the backend. Meaning if it's stateless, even if you work on a set of the commands, still you have this overhead of loading everything up, transforming it a little bit, and then just returning the result and dropping everything and get the new set of data from another user. This is why normally we work with stateful applications, where we just fire up a process for each user, and then we can basically just wait until they go offline. Well, we looked at the overhead that we get with our stateless worker, and the main overhead was actually in parsing JSON. It is a config of 400 kilobyte minified, and then the game state of 30 kilobyte, and it takes 60 milliseconds. If you think about it, like normally in the game, you would say like, OK, 60 milliseconds means like 4 frames, which we actually kind of lose. So on the loading of the game, this is nothing. But when we spoke to our backend guys, they turned from this to this, actually. Saying like 60 milliseconds is too much. We can give you 2. Why are they like this? Are they just like terrible people who just don't want to kind of work together? No, it's actually not the case. The case is basically the scale that we need for such a game. Because if you think about it, if you have 60 milliseconds overhead for each player, meaning that you could have roughly 15 users per second on one core, because you're basically doing some stuff all the time. If you have a couple of million daily active users who play half an hour to an hour, this means that you need lots of servers. You can scale horizontally, but it's actually expensive and it's harder to maintain and operate and so on and so forth. So with 2 milliseconds, this is actually feasible. They say 2 milliseconds, no problems. 60, it's 30 times more than we actually can afford, right? So did we give up? Like, actually, we thought about it. Because like the idea was great and we would have lots of benefit out of it, saying like they won't need to implement all this stuff again and again and again, and they don't have to catch up to us. But if it's technically not possible, then we should consider maybe some different options. However, at some point we Googled, and we found this project, which is actually done by Google, finally. This project is done, Google has an initiative for game developers where they provide some services and frameworks. They trying to attract more game developers to Android platform. This is why they do this. But nevertheless, we could benefit from it, which is a nice thing. So here, the benchmark claims that if you use FlatBuffers, then you spend 0.08 seconds, and if you use JSON, you spend 583 seconds, which is a huge difference in 10,000s, 100,000, something like this. We were intrigued, basically, by this, and tried out ourselves. We didn't get the same, like, tremendous difference, but we actually were able to stick with 2 milliseconds, or a little bit less, which was actually a pretty interesting benefit for us. So we could say like, okay, with this we can actually go and share, go this path of shared code. So what is FlatBuffers? FlatBuffers is an efficient cross-platform serialization library for C++, Java, C#, Go, Python, JavaScript, CPHP, Ruby in progress. We do the game in Unity 3D, so we use C#. So for us, it was actually a good thing directly to start with. How does it work? What you do, you have to define a schema. So basically, you have this table person, which has a name and the age. Table is like a class, basically, and you define its properties. And then you say the root type is person. So you are serializing things, and it can be a complex object graph, but you have to define what is your root type. How does it start? In this simple example, I have only person, so it's really simple. But if I would have, like, for example, contact list, which has an array of people or person tables, then we would just say root type is this address list, and so on and so forth. Makes sense, right? OK, cool. So then what you do, you call a code generator. So you just say -n is for C#. There are all these other things. And you say, this is my schema. FBS is FlatBuffers schema, right? And then you can just use generated code for reading. So here I have a stripped down example of this person class, which is a person class which has extends from table. Table comes from the library itself. And then you can say like, OK, please, I have a static initializer for which gives me this person from a byte buffer. And then I have a getter for name and a getter for age. And this is basically like 2 lines that you would have to use if you would like to get a class and then be able to access these things from a byte array. Then you can suffer through generate code to actually write things. Why suffer? Because it's a little bit cumbersome. It is a little bit cumbersome because, as you can see here, you have also a static initializer to create a person. But what it gives back is actually an offset. So what it does, you create basically a byte array. And then you just add something inside of this byte array, and then you get an offset back. So where is it in the byte array? This is why the name is not a string, it's a string offset. Meaning that if you want to write, you have to do it top to bottom. So you can see it here. I'm creating the FlatBuffer builder. I first create the string, and then I can create the person saying that, OK, the string is actually on the following offset. Then I have to finish this, also internal detail, and then I can get the byte array back. Again, not that hard on a smaller example, but it's actually a bit cumbersome when it comes to bigger examples. So what is underneath? Why is it so fast to read and cumbersome to write? Now, careful. This will be like looking into the matrix. But bear with me. So basically, I will just briefly explain what's inside. You don't have to understand it. It actually just helps you a bit to understand why it's so fast and why it's so difficult to write. Yeah, as I wrote it on this slide. So this is the matrix. So this is the byte array, what we get if we serialize this person. Who can tell me where is the age? Someone? 34, right, here. This is the age, also stayed here, actually. But, like, what's going on here, right? So it's like, it's binary, oh my God. So basically, in the beginning, we say 12. It's just an integer of 32-bit, which is then 4 bytes, and it tells us just like, OK, your first table is 12 bytes ahead. So you go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, bam. This is the starting point of our table. Then here it just say like 8. 8, OK. 8 means that you have, this is a relative position to your virtual table, which tells you which properties you have. OK, 7, 6, 1, this is the starting point, this is the size, this is another size, relative position, and so on and so forth. A little bit of a brain, but the good thing is basically that due to this jumping around, you don't have to, it is really human unreadable, but it's really nicely readable for the computer. So if you have a complex graph, you don't have to parse anything, basically. We just tell through the API what we want, and then internally it just jumps from pointer to pointer, from pointer to pointer, and gets there. This is why it's so fast to read, because it's just loading up the buffer, and then you're just jumping around. This jumping around is basically the same as your runtime doing when you have objects in your whatever object-oriented language. Because there, it's also just pointers into memory, which results into references into something else. Same design, right? So continue with our story of doing this stuff. Did we have to throw away all our JSON files? Actually, no, we didn't. We could just convert JSON into FlatBuffer binary. The good thing is the same FlatBuffers compiler have another option which says like, make it binary, Here is the schema, here is the JSON, and then it will spit out the binary. So what we had to do to transform from JSON to binary was just to write a schema which will confirm to our logical structure of JSON. We had to change our JSON a little bit, but it wasn't a big task. Most of the stuff were actually worked out of the box directly. Then there is also a possibility to go from binary to JSON. This is done basically like this. So if you do this, you'll get this JSON. Make sense? OK. Well, this is great, but how does it cope with change? Because schemas, and basically if I would like to change something, probably everything will break. Actually, it wouldn't, and it was also a very important point for us because specifically in game development, you need lots of resilience for change because game designers, the people who come up with the game idea, the mechanics of the game, balancing of the game, and so on and so forth, like to change their mind. For example, in our case, we have a simulation game with real-time resource management. And in the beginning, we had like 50 types of different resources that you can manage. Then we grew to 120 different resource types which you can manage. Now we're back to 70. Then also we have a battle element inside of the game. I think we are now at iteration 5 of how the battle should work. Actually, so we have to be able to actually change the data all the time, because games are just basically about user experience, and the game designers just see like, okay, this user experience doesn't work, we have to change something so it works again, and people are engaged and interested in the game. So FlatBuffers has an evolution strategy. How does it work? So here is our old friend, the person. And we have a name, which is a string, and the age, which is an int. Now we thought about it and said, like, age is actually a bad idea because you age over time. So it becomes stale pretty quickly, basically after a year. Right? So what would be nice is actually a birthday, which would be a double. So we would like to add a birthday instead of age. What you can do is basically say like age is deprecated, and we add additional birthday. So this is called a non-destructive change. You don't delete stuff, you deprecate them, and then you can add different things to it. Finally, if you would change just the name of it, it won't be a problem in FlatBuffers if you stick to the binary only, because in the binary itself there is no names, it's only offsets. But if you transform them to JSON, then JSON have names again, and then you would have some problems. So generally, to play it safe, always just add new stuff and deprecate old stuff that you don't need. If you would like to keep the order, because you say like I would like to have like logical order of things, I don't want to write everything at the bottom, you could introduce an ID, and then it says where is it like inside of this binary. So it's at position 0, the new one is at position 2, and the old one is at position 1. Okay? So it's backwards and forwards compatible, which means that new code can read old data, and old code can read new data. So backwards compatibility means new code can read old data, right? This is very useful specifically in mobile applications, because you release new stuff, and for example, if you stored some data from the user, you would like your new version to be able to actually still read this stuff. And it could be, and sometimes you also need this old code can read new data if you, for example, a user have 2 devices, and on one she already has a new version, and on another she has still the old version. Meaning it would be nice if they don't crash, right? So in case of, no. So in this case, for example, I'm sorry about that, we would have data which has a person who has a name and an age, and a new device would just ask for a birthday and get a nil, which is then in a way fine. It knows like, okay, I have to put in the birthday, but you would be still able to actually read the age and maybe do migrations by yourself. And an old code which will get name and birthday wouldn't know anything about the birthday, but it would still be able to read the name and would get a nil for the age. So there is still work to do as an application developer, but at least you know that nothing will crash. Everything kind of works. You just have to understand yourself what would you like to do in cases of migrating the data. Okay? So were I completely happy with FlatBuffers? Well, yes, but I wanted to make writing more usable. Because specifically in our simulation game, as it runs on multiple platforms, everything has to be tested. So we have to write lots of unit tests and integration tests. And if you have this very performance-oriented API, it becomes really painful to actually just mock some data out. To say like, this is my config, and I will change just some things so that I can use it in the test. Because it's basically the config is your precondition for the test. Right? So what I did over the Christmas break, I created a FlatBuffer schema editor based on Xtext from Eclipse, so that you can get an Eclipse editor for the schemas, and it can generate code for you. And then I generated eager serialization for C#. What does it mean? So the API becomes much nicer. The API says like, okay, I still have a person, I still have a table, but now the properties are just public properties, name and age. And then I have this static initializer which just gets the byte array, and it will populate these fields from the byte array directly. Then you can change things, and then you just call toByteArray, which will give you a byte array back. Very simple, not as performant as the code which is generated by the initial project by Google, because they are completely trimmed on performance. For me, I wanted to have something which is actually more user-friendly. And basically, this is how you can use it. You just say person from byte array, change the name, and then just serialize it back into byte array. OK, why not bring FlatBuffers to Swift? Because I already have parser, and I already generate code for C#. Why don't get generated for Swift? And I also did that. So then you have something like this, a person to byte array, write it to a file. Everyone is happy. Can also read eager or lazily. Basically, yeah. So is it production ready? Or is it too early for financial sector? Well, definitely too early for financial sector, I would say. As always, it was just created in 2014, sorry. But for example, Facebook is using it in their Android app. If you Google for Facebook and FlatBuffers, you will get a blog post from Facebook. Like actually, if you have some kind of scaling performance problems, Facebook already had it. Like it always feels like it. So basically just Google Facebook and the problem that is like too slow JSON parsing, boom, Facebook already had this problem on Android or something like this. So they actually claim that they switched completely their internal APIs to FlatBuffers, so they can do it fast on their Android client. And here is my naive benchmark for the FlatBuffer Swift. So basically, what I did, I generated random data. Then I used the FlatC compiler to transform it from binary into JSON. Then I minified this JSON. And then I end up with 3.6 megabytes of JSON, which takes 65 milliseconds to parse, which is kind of fine, right? In basically using the NS JSON serializer from the standard one. Then I tried the same thing with the eager FlatBuffers. By the way, FlatBuffers is 2.1 megabyte big, so it's a little bit smaller, right? And it took almost half of the time. Where actually this is an eager serializer, which I think I also did some dumb things inside there. It is possible to make it even faster, actually. What is interesting, though, if you have a lazy initializer, it just takes, what is it, 2 nanoseconds or microseconds? I don't know. So 0.002 milliseconds. So from now on, you can actually already access the data. So there is no parsing involved, and it is really almost zero cost for reading. The writing is also, again, I have to actually elaborate on this. Right now, I'm also like half of the time of the JSON serialization. I think it also can be done much more performant at some point. Right, some rain on FlatBuffers parade. So it's not all good. There are also some problems with it. The interesting part is if I zip the JSON with 3.6 megabytes, I get 639 kilobytes. When I zip the FlatBuffers, which is 2.1 megabyte, I actually get bigger result, which is funny, right? Why is it like this? Well, probably because archiving text is a known problem. So when the zip encoder runs through it, they actually know, through all the redundancies, they actually know how to make it smaller. FlatBuffers looks a little bit random to a typical encoder. Therefore, they don't really know how to handle it, and it seems like they actually do a worse job on compressing them. However, I think that actually if there will be a custom compressor which understands how FlatBuffer works, it could be reduced dramatically and be actually even smaller in a way. Because if we look at the matrix, just a second, where was it? Here. What you can see is most of the data is zeros. So if you have a compressor which understands what to just scrape out the zeros, and then you'll get already into very good state in a way. Right. So Outlook. What is actually interesting about FlatBuffers also, it's not a tree. JSON and XML, as a data structure, it's actually a tree. So you go from the root, and then you can't reference, let's say I have A, B, C, D, E, F, and then I have like such connection. I can't say that this node actually reference this node if it's not on the same branch. Make sense? Kind of, a bit? If you have a graph, it is just generally, it can reference the same nodes. And it can also be cyclical. An example is, let's say I have this person and this person have friends. And it can't have itself as a friend. You wouldn't be able to represent it in JSON, right? Because it's basically a recursive type. If you have a recursive type, it can't be done in a tree. What you only can do is basically referencing this stuff by ID. You have an ID, which represents then the user, and you could say, like, I have friends which are those IDs and not those nodes as they are, so those objects as they are. And with FlatBuffers, you potentially actually can do this, which gives us a different approach on serialization of the object tree, in a way, which we didn't have before. FlatBuffers could also support real streaming, not the XML Zaks streaming, but as we have references, we could actually, and you have, like, let's say 1 GB of data. And you then know, like, OK, I go from here to here, then I jump to here. And I have it in a file. I could just read until here, and then know, OK, I don't have to read all of this garbage. In JSON and XML, you would have to, because there is no other way to understand when the node is actually closing. In here, as you have just a reference, you could just say, like, OK, I read till here. Now I will start reading from here, which makes a real streaming strategy possible because of this referencing things. And it's also very easy to encrypt, because as you saw, it's just numbers. And the only thing that you kind of know is that in the beginning, you have a number which points you to the object. So if you would add a random amount of bytes in front, you wouldn't even know where to start. So this is very, very, very easy way of basically not encrypting, but obscuring the data itself. Because the intruder would need to have the schema and would need to know where to start reading. If you want to encrypt, you can actually also sort all the byte array, and then you also encrypted it, then just basically you need the key to be able to get the initial byte array, and then you still need the schema to be able to actually read this stuff. And about the compression, I already spoke. So again, compression is actually something that slows you down. This is why if you go for performance, you don't compress anyways, because it anyways adds a little bit of the time to you being able to consume things. But if for you it's important to have the smallest memory amount, then you would need a custom compressor, I guess, which is not there yet, but maybe. So, any questions? Yeah.
I have 2 questions. So,
yep.
First of all, you said that you had to change your JSON a bit for it to work with the FlatBuffers. Were the changes? Why did you have to do that?
Yeah. So the question was, what kind of changes did we had to make in the JSON so it works with FlatBuffer schema? Actually, the main change was because of damn resource types. As the game designers can't kind of come up with their mind which kind of resource type they would like to have and what the names are, in JSON what we did, as there is no schema, we just said we have a resource dictionary, we just have a key value. So in our case, it's key amount kind of thing. With schema, we would have to kind of nail it down and say, like, this is the numbers. So this is like, this resource has to be named like this. And if you change it, we have to deprecate it, add another one, deprecate it, add another one, and so on and so forth. So in this case, we said, like, OK, game designers still need this freedom. So what is a dictionary? It's an array of key value pairs. So what we did is basically we switched from a dictionary to array of objects, which has just a key, like key and amount properties inside of it. To make this also perform and to read, what we do is basically we sort them. And then when we want to access them, we know it's a vector with following key values. Then we just get the key, we do a binary search to find the right one, and it's the same. So generally, if you think about it from the logarithmical standpoint, it's the same as a dictionary, because normally dictionaries, the average case is log n to find something. And in the binary search, it's also log n, average. Not in the best case, it's 1, but it's about your keys, and if it's a binary tree, or is it another talk.
The other question is, why was the birthday a double?
Birthday?
Yeah.
Why was the birthday a double? Actually, I took it from NS date. If you get the NS date into time, then you get a double. Normally, we actually use it as, normally you use it as a long. So it's like Jesus ticks. So how much time did it took to actually to this point. But funnily, in the NS foundations, it's actually a double. So I took it as a double. Any more questions? Yeah.
So JSON is readable, so it makes easier to discover the APIs, right? So if you don't have really defined the API, you just want to just play with it, check what's available and not. JSON is great, you can see the results. So aren't FlatBuffers like making it more difficult?
With FlatBuffers, what you would just need to see is the schema. So the backend will, let's say Twitter. They provide us with a schema. I think it's even better than discover it by yourself, like actually downloading this thing and then just going through yourself. Because actually the schema is a contract between backend and the front end. So in a way, if it's nicely written, it can also have some comments inside of it and so on and so forth. So it's actually like, they would lose a little bit of flexibility, meaning that if they would like to introduce new stuff, they would have additive change, as I explained in the evolution of data. But again, for us, it would be better, because we know what to expect. It's not like they just rename the key and my front end is just crashing because I can't find this stuff anymore. Okay. Yeah.
Could you tell us what kind of game have you been developing, and was it delay sensitive, so you decided to use these FlatBuffers?
I didn't get the last point.
Was your game response time delay sensitive, so you decided to go with FlatBuffers?
Yeah. So basically, the game what I'm working on currently is real-time resource management game. It's not out yet, so it will be out in later this year. This is why I can't just point it out. But again, the point is that we needed this response time because it is real time, and we will send lots of commands every second, basically, and we decided with backend that we will send the commands in a bunch for 20 seconds, 30 seconds. But actually, every 30 seconds, backend has something to do. Meaning that it's basically pretty much spammed with lots of stuff. And if you have, we go for like one of our titles, which we took as an example how much DIU we could have 2 million daily active users, meaning that if you start to crunching the numbers, you would like to serve up to, I don't know, couple of thousand players on one CPU. Otherwise, it becomes really expensive in the horizontal scaling approach. This is why we had to look for a more performant alternative, basically. Because again, when we were doing the game without the backend, we were totally happy with JSON. Because you read this stuff in the beginning of the game, you anyways have a loading screen, and if you compare it with, I don't know, some textures which you have to load, which goes in 50 megabytes of images, then this kind of 400 kilobyte of JSON, which will be parsed, yeah, 60 milliseconds, whatever. But if you actually move this part of the application to the backend, then it starts getting critical and tough to do. Any more questions? Yeah.
You said about using FlatBuffers to serialization during the network communication. But, does it make sense to use the FlatBuffers in serialization to database, like storing the objects in FlatBuffer format as binary blobs in the database and so on? Is it usable?
Yeah, the question was like for communication, FlatBuffers make sense. What about storing this stuff into a database? Funny story. Actually, our backend translates the FlatBuffers at the end of the session into JSON and stores it in Postgres, because Postgres has actually a query language for JSON, so that they can actually, because otherwise it's just a binary blob. You could still store it as a binary blob, as a blob basically, but the problem is then you won't be able to query it. If you need this, like it is dependent on the use case. Sometimes you also don't really need to query this. In some cases you just say like, okay, I would like just store some data, this is fine. If I need to run a batch on it, then I will anyways go through everything and do, for example, data migration to say to new versions and so on and so forth. But if you would like to be able to query what's inside of the game state, then JSON is better, because it can be, like if there would be a plugin for Postgres into reading FlatBuffers, then you would have any problems. But there is no such plugin yet. Because also JSON was, I think this plugin is pretty much recent. Before, if you would store JSON, it would be just clop. It's like char object, which is just big. I haven't, like, and you can't like query it. There is actually a name for large text in databases, but I forgot. Never mind. Any more questions? Then thank you very much.